Okay, so the final exam is cumulative. Pretty much all the syllabus that we have done so far is going to be part of this exam. But if you really notice carefully, it's like most of the syllabus of this class was kind of like done by exam two already. After exam two, we did CISA tool, but CISA tool is, I mean, MATLAB in general is not allowed in the exam. So CISA tool you can't do. And then the second thing is after the exam, we did the body plot related stuff. It's just a small fraction. Primarily, most of the core content of the class was exam two. And exam two did include stuff from the previous part as well, except for the modeling. So one can say that the final exam is basically equal to exam two plus the modeling stuff from the previous plus the body plot stuff from the last homework. So this is the previous stuff. This involved mechanical and electrical stuff. And again, I want to, like this body plot related controller design is technically the part of the next class. It's not part of this class. So I'm not going to focus on this too much. It's not going to be a huge fraction of the exam. It'll be like one-ish questions. So we'll see about this. But primarily, I'm interested in question number one, question number two, and question number three of the homework number. It's a 13 is the last homework, right? So those are the main things I'll be asking about. So I won't ask anything about Nyquist stability criteria, no Nyquist plot, just how to plot body plots and how to interpret body plots. That's kind of like the main, right? So let's talk about the structure of the exam. So exam is going to have question number one. See, the gist of this class is controller design. That's my main focus. So question number one is going to be controller design problem. Kind of like your exam one, it wasn't too tough. I hope you watched the solutions I posted for the exam one, or you were here. So kind of like your exam two, sorry. So the solutions I posted for exam two, I went over a controller design problem, which was simple-ish. So it could be this, and then there would be one more controller design problem. I'll call this more of a medium difficulty level. And then the remaining questions are all, this will be like easier. It will be like, I'll call it medium to hard. Yes. The remaining is auto-graded stuff. The remainder of the exam shall be auto-graded. This means mostly multiple choice questions, but sometimes it will also be enter the number, or it could be like, enter few words. No essays for sure. That's kind of like that, yeah. And as I said, the syllabus of the class is, syllabus of this exam is everything. Oh, yes, sir.
Just for exam one, split half 40 points for non-auto graded, 40 points for auto graded. Exam two, it's now 50-30.
Yeah,
What is it looking like for the final, or we don't?
yeah, it'll be like, these will be like 20 points, 20 points. And I think this is gonna be like 60 points or something. 60-ish. Yep. So, yeah. I mean, the point I focus on controller design because they pretty much involve all the concepts of the class in one single go. So they are like, my favorite problem to ask. They combine everything. So let's look at the syllabus once again, a deeper look, all the topics that we have covered so far. So we have talked about, in the very beginning, we'll talk about differential equations. The reason we talk about differential equations because plant is a differential equation, controller is a differential equation, sensor is a differential equation, pre-filter is a differential equation. The whole control block diagram of a control design system is all just combination of differential equations. But we don't just do differential equations, we do Laplace, and after Laplacing the linear differential equations, they become transfer functions. So you should be able to go back and forth between transfer function and differential equation really fast. So that was one of the first concept we learned. And as a sub part of this, we talked about how to plot the responses of transfer function. Specifically, we focused on step responses a lot. We talked about ramp response, sinusoidal response, which became the Bode plot. We talked about the impulse response, all of those, but we focused the most on the step responses of the transfer function. And specifically, we talked about the first order systems. We have talked about the second order systems. These are the most important transfer functions, and the step responses are the most important because controller design is built on that. But then we also talked about what would happen if you put zeros in the system. Zeros make the response faster and higher overshoot. And what happens if you put more poles in the system? And we also talked about the dominant pole stuff. So dominant poles or dominant zeros are the ones which are more closer to the origin in the real part. That was the first big chunk of the class, just differential equations because they are the building blocks and what are the solutions or the responses of those differential equations. Then the next step we talked about, okay, I get it. Control system is just primarily just combination of differential equations, but where do you get those differential equations from? That was the modeling part. In real life, whenever you do controller design, modeling is the one that takes most of the time. Most of the time is spent in modeling actually. And modeling means for a given system, find the differential equation for it. Once you have the differential equation, controller design is usually faster. You can do that in like half an hour, like your exam. So in the modeling, we talked about mechanical systems. They were the linear or translational mechanical system, and then the rotational mechanical system. We specifically talked about how if you're sticking to linear systems, then the mechanical systems could always be boiled down to combination of spring and some mass and some damper, or the rotational version. So rotational spring, rotational mass, which is moment of inertia, and rotational damper. So it's going to be all combination of this. Particularly, we talked about this 8 types of problems. So these were the problems which had 1 degree of freedom or 2 degree of freedom. We did this problem, either with a platform or without platform. And especially for the 2 degree of freedom system, we talked about doing this problem with the absolute or relative coordinates. So that's the stuff from the previous stuff. We did 8 type of mechanical problems. And of course, I'm not going to give you anything more than that. Like, this is pretty much all the problems I'm going to do will be combination of just these 8 problems. And we also talked about the mechanicals and then electrical system modeling. For electrical system, we did 1 loop system, which is equivalent to 1 degree of freedom system or 2 loop system. And now we model things with resistors and capacitors and inductors. But once you do a Laplace version of this, they all basically follows the same Ohm's law. So the voltage difference across each of them is their impedance, which is these numbers, multiplied by the current that is passing through it. They all follow pretty much like a Ohm's law if you work in the S domain. So when it comes to electrical system, just directly work in the S domain. It's kind of like you're dealing with the resistor circuit. Capacitor inductors, their differences just fade away in the S domain. So we talked about those. And then of course, there was motor. The motor has a electrical side and the motor has a mechanical side. You can put a lot of stuff on the mechanical side, including gears if you want to. And then you can also put a lot of stuff on the electrical side, like extra capacitors or resistors. But this will handle by the electrical logic. We'll do KVL and KCL. This side will handle by the mechanical system logic. But what connected the 2 parts together? And that was this, that when the mechanical shaft of the motor is rotating, it produces some back EMF, which is proportional to how fast is the shaft rotating. And when you pass some current through the system, it's going to apply a mechanical torque, and that torque is the motor torque constant multiplied by the current. And back EMF constant, torque constants are same usually because of energy conservation. So that was the idea about the modeling. So make sure you review those 8 type of problems and 1 or 2 loop systems over here, and motors with some gear combinations, things like that. That's after talking about modeling. All right, now we know how to handle differential equations. Now we know how to get differential equations. Then we delved into the controller design principles. So this is precursor to controller design. Before you start designing controllers, there were a couple of things you gotta, learn how to manage. The first one was just the structure of the controller. The most general structure we talked about in this class is following, where you get to design 2 things, pre-filter and controller. We call it 2 degree of freedom. And then you could potentially have a disturbance affecting your system. This is G, this is the output Y, and then you could have some sensor. If H is 1, we'll call it a unity feedback system. So this was the most general structure we talked about. And so this is a block diagram. It's a combination of many blocks. Each block is like a differential equation or a transfer function. And the idea was that we are given the value of G, we are given the value of H. We choose a sensor and then that's fixed. The plant is given to us. Yep. These are the 2 things that we get to design, but we don't care about any of those things. We care about the overall system like this. So the overall system could be written like this. It is FGK over 1 plus GKH times the reference. This is the transfer function from a reference to output. We also call it closed loop transfer function. And then the disturbance multiplied by G over 1 plus GKH. This is a transfer function from disturbance to output. So the output depends upon the 2 overall inputs which are falling into the system. So you can reduce this block diagram into 2 blocks, one relating R to Y, one relating disturbance to Y. This was our most loved system. We are given the value of G and H. We want to design the value of F and K in such a way that when you give a reference command, it gives a right response. We also want to plan for this, that when you give a disturbance, this transfer function gives a 0 response. That's what we would prefer. Like if you have a disturbance, the disturbance should not affect the output. So this transfer function's response should go to 0. This transfer function's response should follow whatever the reference command is doing. That was the first thing we talked about, the block diagram structure and then how to reduce it. This is a reduction of it. And then we learned a little bit more about this closed loop transfer function. The closed loop transfer function's zeros, I'll call it CLZs, closed loop zeros of this transfer function. They were the zeros of F and G and K, but also the poles of this H part, like this. And then the closed loop poles, they were the poles of pre-filter. And then whatever the root locus of GKH gives us. So that's first step. We spent a lot of time on this. And by the way, another type of terminology, just GKH is called open loop transfer function. It's also known as loop transfer. So we talked about this because ultimately, we talked about the design of the controller is all about making Y equal to R. So given this, design this so that Y behaves like R despite the presence of disturbance. And that behavior of Y given some R ultimately depend upon this. That behavior of Y given some disturbance depends upon this. So it was important to understand these transfer functions. So we did that. And in the similar vein, precursor to controller design, the next thing we talked about, okay, what do we want Y to do? We don't want Y to go to infinity. That was the one thing. We called it stability. This basically means the closed loop poles They are in left half plane, they are negative. And we can check that using a route table. And I only care about the simplest route table because we have computers now. We're not living in 1800s. And then root locus actually is a great way to check if the closed loop poles are in the left plane. This is the one we use the most. Root locus tells you where the closed loop poles are going to be. Root locus of open loop transfer function tells you about the closed loop poles. You can just check it from there. And so that's first thing. We don't want the output to go to infinity. And then we also want the output to ultimately become equal to R in the as time goes to infinity. We call it low error. And we had three formulae for it. So I gave you three most general formula. One formula for was one for step reference command, one for a ramp reference command, and one was for step disturbance. The most general formulae which were given to you, this formula was true when the limit of f is equal to limit of h. This formula, the most general one I gave you, was true when the whole of f is equal to whole of h. This was for any f, any h. This was the most general formula anyway. So I gave you three formulae. Learn to remember that this was the most important part. Learn the assumptions of those formulae. And then what was the end result of all these formulae? The end result was either the controller needs integrator or double integrator, or the controller needs some sort of gain, or the combination of these two. This is what all the error formula boils down to. Because if you look into the step error formula or the ramp error formula or the disturbance error formula, the controller always lied in the denominator of those things. So if you make the controller high gain, or if you put an integrator, that's going to make the DC gain infinity, then it reduces the error. High gain, this is the DC gain part of it. So that was the error calculations. This is perhaps the mathiest part of this whole course. Deriving these error formulae and using them and understanding their assumptions. And then after that, we talked about, okay, y is not going to infinity, you're stable. Y is ultimately becoming equal to R, so you have reached what you wanted. But even along the way, so we talked about some transient specifications. We talked about settling time, we talked about percentage overshoot, also written as MP. These are not the only specifications. We also have rise time, peak time, overall error, maximum value of the error, integral of the error. There are like 100 different specifications you can cook up, but two are good enough. I only primarily talked about settling time and overshoot. So we talked about these specifications, and the idea was that if you want to have right settling time and right overshoot, you want the closed loop holes in some region. If you want smaller settling time, the closed loop holes should be negative. If you want smaller overshoot, the closed loop holes should be less angly. So these were the regions we typically get for settling time and overshoot. And these regions are only true if the closed loop transfer function was first order or second order. Those were the rules. And there were no zeros in them. And second order, I mean second order underdamped, which means either this effectively boils down to that the closed loop system would either be one pole system or the closed loop pole is two complex pole system. If the closed loop system has just one pole or the closed loop system has two poles in it like this, then these regions are true. What happens if these conditions are not met? Well, we know like what do an extra zero will do to the system, what will extra poles to the system, and then we're just watchful of that. And then in the similar way, for transient specifications, we talked about root locus. And the idea was that the root locus plot of GKH gives you the closed loop poles, not all of them. Closed loop poles are the what the root locus gives you and also what you put inside the prefilter. What you put inside the prefilter is both a closed loop pole and the zeros of the prefilter are the closed loop zeros. So prefilter is directly affecting the closed loop system, but root locus gives you the main closed loop poles. And we talked about the rules for plotting, and I'm going to request you to review them. But most important is remember those basic root locus diagrams. that's where, that's where the intuition for controller design comes up. Okay. This is it. After that, we just did controller design. So now it's time to combine all these concepts together. And we talked about controller design. And this is an example I'm about to do right now. After controller design, we talked about CISR tool. Don't worry about that. You're not allowed to use that in the exam. And then the body plot stuff. Just master the question number 1, 2, 3 of the homework. I'm not going to give you any more surprises beyond it. So this is like a quick overview of the course. We talked about differential equations, how to get them. And then we started talking about, okay, I really want to design controllers. But before I start designing controllers, let's understand the structure and some terminology and these things. And let's learn about stability, low error, and transient specifications, which root locus will help us satisfy. And then we'll throw all of these things together and design a controller. Okay. That's kind of like the gist of the whole class. Now, before I go on and do a problem for you guys, ask any questions. Yes, sir.
Considering that the two short, well, like three response parts, both done, both designed, are we going to be getting a modeling problem that's like
Yeah,
a string of, it's gonna be a,
I'll
s- gonna be a string of multiple choice questions, like,
Right. So the modeling, there will be some modeling problems, of course, but I'll put the modeling problem as this. What that means is like, I can't give you like a full ass modeling problem.
So it's gonna be like this tiny little.
It's gonna be like tiny parts of it. Like, for example, in the first exam, there was a modeling problem. I give you a system and you're supposed to find the transfer function. I can't do that in multiple choice. So I'll break it up. Like, I'll be like, hey, draw me the free body diagram of this or something, some way. Or like, what are the forces acting on this particular object? Or if these are the forces acting, what will be the transfer function out of those? Like, I'll split it into multiple pieces. Or I'll give you like some really simple version of it and then tell, is this correct or not? There are many ways to make it a multiple choicey. Yes.
With that bottom part of the page where you had the row to the right.
Wait, did you have the same thing? What was your question? What?
Yeah.
Oh, okay. I see. Do you want my cone? I snatched it from a squirrel today.
Wrong page,
It's the wrong page.
or the rotating systems.
Yes, sir.
There was some talk about this exam being online again. Is it we have to be here?
That
or-
I'll discuss with you guys after this is over. After I'm done doing one problem, that's the main thing I want to discuss with you guys. Yes, sir. Say again? Wait, I thought I already did. Shit. Okay, I'll fix that thing. Actually, I'll fix it right after this is over.
Like an ambulance out there.
What'd you say?
It's like an ambulance out there.
There's an ambulance out there?
I don't know why.
Must be the exam times. Okay, all right, so let's do a controller. Oh, yes, sir.
Yeah, how long would the exam be?
Yeah, I'll discuss all those logistics with you once I'm done with this. Okay, so let's do one controller design problem because that apparently seems to be the focus. And I'm gonna do like a hardish, medium hardish problem for you guys, not an easy one. And then let's see how that goes. Let's say that you have some first order system. You give it some input, you get some output. Can you give me example of some first order system and what the input and output of that would be? You should know this by now. At least one. Sure. Yes. So what is the input? What's the output of that system? It's mu.
Sorry, I read that as you.
No, as in like, what's the name of that signal? Yes, input is U and output is Y, but like voltage to what? Voltage to speed of a motor is a first order system. Voltage to speed of some toy car is like a first order system. There's so many first order systems we can make up. So today we'll have a first order system once again. We'll call it 1/s+2 like this. And then we take the output Y and there's a sensor that's measuring it. But the sensor has its own dynamics to it. And we'll say the sensor dynamics is 10/s+10. Something like this. Okay. So this basically means, it's a first order system. So if you give it like a step input, it's going to have that first order response. It will build up slowly. If you give it a step input, it's going to reach half the value because the DC gain is 1/2 in about 4/2 seconds. So if you give a step input to your plant, the output is going to start from 0 and build up to half the value of that input because the DC gain is half. And then it's going to reach the final value in about 4/2 seconds. Similarly, this is step input. If you give some sort of, this is first order system. If you give some sort of input to it, like the output is a constant, the sensor would slowly give an output, which will start from 0 and build up to it. The DC gain is 1, so it's going to build up to the same value which you're feeding it. And it's going to reach the final value in like 4/10 seconds, so 0.4 seconds. Basically, if you give any kind of input to the sensor is going to reach that input in about 0.4-ish seconds. And then, but it would reach that input. So that's what this sensor is doing. It's building up. If you give some measurement to it, it's going to build up to that measurement in a little bit. Okay. So then you take this. You're fully allowed to use pre-filter if you want to. And then controller is what you're going to design. Yes. So here are your specifications for which we want to design. First one, if the reference command is step, then the error in steady state should be equal to 0, which basically means if you give a R of some value, let's say 2, you'll reach the same value of Y as t goes to infinity. That. If the reference command is a ramp, which means you want the output to linearly increase, the reference command is a ramp, output you want to linearly increase, then I request the steady state error is like less than, we'll make some number up, 0.1. I may adjust this towards the end, but the idea is this. So if the reference command is constant, the Y should follow that constant. If the reference command is linear, the output Y should try to approach it, but it's allowed to have some offset from it. That's the meaning of this. And then if R is step, I want settling time to be less than, let's say, 1 second. Why not? And then we want overshoot to be as small as possible usually. But let's just say I want the overshoot to be less than 2%. Okay. So those are some of my specifications. And then there is one more specification which doesn't follow it. See, stability is a specification which is said without saying it. Unless your whole system is stable, oh, you're not going to get any error, 0 error. Your errors will be infinite. You won't get any settling time and overshoot. All these things are only possible if the whole system is stable. So stability goes without saying. Okay. So these are the steady error specifications, transient specifications, but we talked about other specifications too. So make the U small. Now making the U small, there is no formula for it. We typically have to experiment with MATLAB. So I can't ask you in the exam, can you please make the U less than 8? That would be too hard for you to do by hand in the exam. So the only thing I can ask in the exam is, I don't know, make it finite. So make sure the U is finite for step reference command and the ramp reference command. So those are our specifications. Let's start designing the controller. Whenever we start the controller design process, first we handle the error specifications. Why? Because we have formulae for them and they give you something hard and fast to work with. And then we talk about the regions for these specifications, and then we use root locus to realize what should be the controller, they'll get me the poles in the right region, and then we just find that controller. So that's the same process that works for all controller design problems. This will tell you what you need in the controller for sure. You put that into the controller, these specifications are met, and you're good to go. This will tell you where you want the closed loop poles to be, assuming the closed loop system is first or second order, where you want your closed loop poles to be. Well, once you have made the closed loop poles in the right region, it'll tell you what kind of root locus analysis will tell you what kind of controller will get the job done. And then you just do some math to figure out all the unknown parameters in that controller. Okay. So that's it. Let's solve this one. First, the error in steady state, you do a step input. So error in steady state for a step reference command. The condition was that the limit of pre-filter should be same as limit of H. This is limit S goes to 0, also known as DC gain. So when this is true, this would be equal to the value of the reference command in time domain, the actual value of your constant step reference command divided by 1 plus limit S goes to 0 of G and K and H. I want this error to be equal to 0. This implies I want the limit of GKH to go to infinity. That's the only way this error is going to be equal to 0. This implies I need 1 over S in G or K or H. G doesn't have 1 over S in it. K doesn't have, sorry, H doesn't have 1 over S in it. Therefore, K needs 1 over S. That's what I was trying to say. When you do the error calculations, usually it boils down to does your controller need indicators or not? Does your controller need some high gains or not? That's what it boils down. Yes, sir.
How much work should we show?
This is good enough work. If anybody is trying to derive this formula from scratch, you know, Jesus loves you. You don't need that much love in the exam. But this is good enough. Okay, so the next step is error in steady state due to a ramp reference command. Now this formula, the one I gave you, is only true when the whole of the pre-filter is equal to whole of the H. Is there a formula when pre-filter is not equal to H? Yes, there is. I just didn't tell that to you. Like for example, there is a version of the formula where it would be whatever this formula tells you plus 1 divided by the pole of the pre-filter. That's the total ramp error. There's a formula like this. You can derive it if you want to, but let's reserve that for next class perhaps. So this would be equal to the slope of the ramp, whatever it is, divided by, which by default is 1, divided by limit of S times G times K times H. That's your formula. So I want, there's no defaults, there's no slope given. So default slope is 1. So like R is equal to T. If R was equal to 2T, then the slope is 2. So like that. If R equal to 3T, the slope is 3. And this is by default 1. The step is 1 by default. Otherwise, I can say the step is like going from 0 to 2 or 0 to 3, whatever. So this is what we have. Limit of SGKH. So this should be equal to G is 1 over S plus 2. Controller, I don't know. H is 10 over S plus 10. All that stuff should be less than 0.1. That's the logic. Okay. So let's plug in S equal to 0 in all the places where I can safely do so. Like if I plug S equal to 0 over here, it's going to become 10 over 10, 1. If I plug S equal to 0, this is going to just become half. But I can't plug S equal to 0 over here yet, because I don't know what controller might have. Controller might cancel that S equal to 0. So we don't know that. So all the safe places, you can put your S equal to 0. So this will basically boil down to limit of S goes to 0 of S times your controller. And this is going to become 1/2. This is going to become 1. This is supposed to be larger than 10. So that will become 20. This is math. This is beneath me. You'll figure it out. Okay. So this is a condition I want. And as long as the limit S goes to 0 of S times K is larger than 20, you are good to go. Well, how are we going to do that? Well, first of all, the controller needs 1 over s, because if the controller doesn't have 1 over s in it, then this limit is just going to go to 0 because of this s sitting in there. And 0 is not larger than 20. So the only option is that the controller has 1 over s in it or more, and then some extra stuff like this. Okay, so I'm going to call it 1 over s multiplied by the extra controller. So s times k is basically canceling this 1 over s and taking the extra controller. So the DC gain limit s goes to 0 of that extra controller, that should be larger than 20. And this is the number that you put inside the Citroen's toolbox. So these are my error calculations. My error calculation says that the controller needs 1 over s, and the remaining controller beyond that 1 over s should have a DC gain larger than 20. Some people would be like, hey, let's just throw in another 1 over s in the controller. If you put like 1 over s square in the controller, it would definitely meet this specification. If you put 1 over s square in the controller, then one of the s will cancel off. The remaining stuff has a 1 over s left, and the limit of that is going to be infinity. Infinity is larger than 20. So if you try to put 1 over s square in the controller, you will get your RAM error 0, which is of course less than 0.1. But you know, if you put 1 over s square in the controller, then your root locus would look trickier. Having a 0 in the root locus pulls it to the left. Having a pole in the root locus pushes towards the right. So if you put a 1 over s in the controller, it's going to push the root locus to the right, making your settling time harder. If you put 1 over s square in the controller, your root locus is going to become even harder to do. So usually it's not a best idea to overdo on the specifications, but sometimes it's okay. Like if the controller was requiring way too much gain, then maybe it's just worth to make the error 0 by putting double integrators in it. But usually we try not to overdo on the specifications because they are trade-offs. To give something, you have to lose some. To get something, you have to lose something. Okay, so the error calculations are basically saying I need 1 over s in the controller, and I need the DC gain of the rest of the controller to be larger than 20. So we will watch out for that. And this error is only true when f is equal to h. Okay, so here we go. Now let's do the transient specifications. So if closed loop transfer function is one pole or two complex pole system, if this is how your closed loop system looks like and no zeros in it, then we have done this like a gazillion times. This will basically boil down to that the closed loop poles should be more negative than 4 over 1. They should be more negative than -4. And the overshoot, we have a formula for it. E to the power minus pi cotangent of the angle should be less than 2%. And then you take log on both sides, minus pi cotangent beta should be less than ln of 2 over 100. And then divide by minus pi, that's gonna change the sign of the inequality, because when you divide by negative stuff, the inequality changes sign. And then you do cotangent inverse, and that's going to change the sign again because cotangent inverse is a decreasing function. So ln of 2 over 100 divided by minus pi, whatever that angle comes out to be, I don't know. Can somebody do this, please? What is ln of 2 over 100 divided by minus pi cotangent inverse? I'll do it.
38.8.
Oh, wow. Hey,
It's on Zoom.
I'll take it. Yes. I'll trust this. 38.8. If you're wrong, we'll blame.
Has every lecture been on Zoom? Okay. It doesn't really matter, it's just like,
So this is kind of like the region we want to be in. So settling time was 4 over real part. If you want settling time 4 over real part, so real part should be larger than 4 over settling time. So here we go, we got the region. Okay, people. Now this is just like, basic stuff. I'm building towards it. I got my basic math down. Now comes the thinking part. I've done my error specification, this specification. Actually, wait a minute. let's do this use specification too. What do you need to make U finite? Let's say reference command is a step. What do you need to make U finite?
It has to be proper.
Okay, so U finite for step response. Basically, the K cannot have more zeros than pole unless there is a pre-filter. So basically the rule boils down to that F times K cannot have more zeros than poles. And similarly, if you want to keep U finite for ramp, then F times K cannot have, can you guess what this would be? This was part of one of the homework problems. So if you want to keep U finite for a step input, I need to make sure if there is no pre-filter, I got to make sure controller doesn't have more zeros than poles. If there is a pre-filter that can help with it, so in net, controller multiplied by pre-filter cannot have more zeros than pole. So controller can have one more zero, but the pre-filter will have to have one pole. Controller have two extra zeros, but the pre-filter need to have like two extra poles in it. So what comes out for a ramp one? Yes, sir.
Can't have one extra
Your
zero.
own restriction, I think.
No, there is restrictions.
They can have one extra zero.
They can have one extra zero. Cannot have more than one extra zero. Then. So that's kind of like the proof of this is done in the past lecture videos. If I have time left, I'll explain about this proof. But it is what it is so far. Just remember this. Roughly, it boils down to this. I know the R signal is passing through a pre-filter, and then it's getting subtracted from something, and then it's passing through a controller. A pole in the transfer function, when you convert it back to original differential equation, it leads to integration. A zero in a transfer function, when you convert into time domain, becomes differentiation. So how many zeros you have compared to the poles is basically means how many more differentiation you're doing. If you have a step signal, like if reference command is a step, if you do a derivative of a step, it goes to infinity. So if the number of poles and zeros, if the number of zeros is more than the number of poles in these two terms, then that means you're doing more derivatives than integrations. In net, you're going to do derivative and the U is going to go to infinity. If R is a ramp like this, you can do the first derivative. The first derivative of a ramp is step, but you cannot do second derivative. So you're allowed to have one derivative in F and K. You're allowed to have one more zero in F and K. That's a little bit more detailed to the rule. But if you are looking for a little bit more fleshed out detail, how the zeros in controller or pre-filter lead to differentiation in time domain, just convert those transfer function back into time domain and see. Or refer back to those lectures. But this is kind of like the end result. Okay, so I have all the basic ingredients done for all the specifications. Now it's time to try root locus and see what kind of controller will do. So here is my first question for you. So I'm about to do the root locus analysis. The whole purpose of root locus analysis to see what kind of controller would actually get the job done. So I should try what is the simplest controller I can try. Oh. So I need 1 over S in the controller, and because of that error requirement. So I'm going to try a controller which has some gain, because the root locus job is to change the gain of the controller and show me how the closed loop poles will move around. I'll try a controller with an integrator. What kind of pre-filter should I try? Usually we start with no pre-filter. What do you guys think?
And for S filter.
That is correct. If you're gonna pay respect to this error formula, your F better be equal to H. Actually, this is a good thing and a bad, I mean, it's bad thing because, you might miss it out. But the good thing is, it's kind of like, when you're a vegetarian, like when you go to a restaurant and they only have like one veggie option, it's a good thing. Now I don't have to think too much. So it's the same thing. Like, once you're gonna use this formula, you know that I'm only gonna use F is equal to H. No need to think too much. That kind of takes it away from you. So F has to be equal to H. This is for the error specs. So F has to be equal to H, which is 10 over S plus 10. I'm not going to be able to touch prefilter anymore. Anything I have to do has to be done in the controller by itself. So that kind of like, gives less things to worry about basically. That's cool. So I'm going to try this. Whose root locus do we draw? Prefilter does not enter the root locus at all. We're going to draw the root locus of GKH. Does prefilter affect the closed loop system? Yes. Prefilter is like sitting right there in series. Whatever you put in zeros will become the closed loop zeros. Whatever you put as a pole over here is going to become the closed loop pole. It affects, but it doesn't affect the root locus. Root locus only gives the poles of this combination. Okay. So we'll do the root locus of GKH. Well, G is 1 over S plus 2. Controller has 1 over S in it. The gain will be taken care by root locus. And then H is 10 over S plus 10, like this. Okay. So I'm going to do the root locus of this transfer function. Let's see how that looks like. So I have a pole at origin, pole at -2, and then a pole at -10. This is like so dominant, it's not even going to matter much. But how will the root locus look like for this one? Whenever you want to plot, first of all, this is one of the basic 7 or 8 root locuses. This should be just memorized. There's no point to like, try to do this again and again. Those 7 or 8 basic root locuses, which are in the things to remember, just remember it. This is one of those. Otherwise, well, according to the left-right rule, no root locus here, there'll be root locus here, no root locus here, root locus here. And 3 poles, no zeros, there'll be 3 asymptotes. 3 asymptotes are going to be -infinity and 60 degrees and -60 degrees. And the center of the asymptote is going to be the average of the 3 poles. It's going to be somewhere over here. So there'll be 3 asymptotes like this. And then this pole is already following its asymptote, great for it. And these 2 poles will come together, touch briefly, and then move along their asymptotes. So that's the idea. So what is this root locus telling me? It's telling me that as I try this controller and I change the gain value of this controller, then the closed loop poles of this part, prefilter are also closed loop poles. The closed loop poles of this part will start from here, go like this, and then do like this. And this will go like this. From 0 to infinity, as the gain changes, the closed loop poles will be moving like this. So what do you guys think? Will this get the job done? Will this give me my specifications? The answer is no, because I wanted the poles to be more negative than -4. I wanted the poles to be in this region. No matter what I do, this pole is in this region, but the dominant poles are these. So my closed loop system is 3 poles from here, 1 pole from the prefilter. Closed loop system is a 4th order system. 1 pole like this, other pole like this, 3rd pole like this, and the 4th pole is coming from the prefilter. So great, but my dominant poles, which are the most important ones, they're never in this region. So what should I do? What's my most favorite trick ever? So because you see, my closed loop system right now is 4th order. 1, 2, 3. 4th pole is coming from the prefilter. How many closed loop zeros do we have, by the way?
0.
They are zeros of F, none. Zeros of G, none. Zeros of controller, none. Poles of H. I have 1 closed loop 0. Okay. By the way, where is that 1 closed loop 0? That's a pole of H, -10. Where is one of the 4th poles? Right there at -10. So one of the closed loop zeros is actually canceling the one of the closed loop pole. Effectively, you have a 3rd order system, and this is what it is. 3 poles. So one of the closed loop zeros, that's basically the pole of H. This is -10. The four closed loop poles, three are from the root locus, one is from the prefilter. The pole from the prefilter is basically -10. So there's a closed loop zero and closed loop pole both at -10. They are canceling off each other. So effectively, my closed loop system is a third order system with no zeros. But if you really want to think about it, the third pole is rather non-dominant. It's like -10 and beyond. The other two poles live like this. So it's pretty close to a second order system. I am totally okay to use my formula if I want to. Okay, more on this later. All I know is this is not going to get the job done. So my favorite technique is whenever system is too complicated, whenever your life gets too complicated, what do? You cut off people in your life. And that's what we're gonna do. So we're gonna cut off some stuff in our life. And the next controller we're gonna try is, I need that integrator in there for sure. Yeah, what should I do? Where should I put my zero?
Negative.
If you put zero over here, that's not gonna help. That's just gonna go like this. Root locus will go like this. If you put zero over here, then the root locus is gonna come together and go like this. Okay, so I'm gonna try a controller of this type. So you put a 0 at 2. This controller is called a PI controller, proportional integral controller. Okay, so let's try this controller. Now I'm gonna do the root locus of 1 over s plus 2, and then s plus 2 over s, and then 10 over s plus 10. That's a root locus. So let's do it all. So pole at origin, pole at -2. There's like a 0 right there at -2. And then there is a pole at -10. So if you really draw the root locus, you will notice that actually, if you secretly keep it very nice, detailed, then these two poles will come together over here. They'll do a small circle thingy. One will go to the 0, the other closed loop pole will here. These two will come together and they will shoot up at -5. You can even ignore this little bump over there, but roughly what's happening is one closed loop pole starts from here, do this little circle thing, it goes to closed loop 0. So there is a closed loop pole that starts from this X and go to the 0, but the closed loop pole is right here itself. The other, so you can just ignore it because that closed loop pole and that 0 cancel each other. It's this closed loop pole. This is the root locus you can look at. Will this get the job done?
Maybe.
We have to check that.
Why do you say maybe?
This could be right before the.
I mean, like I wanted more negative than -4. So I can, when the gain is really small, the closed loop poles are here. When the gain becomes larger, the closed loop pole will be here. I can make the gains large enough that they can get into this region. So why do you say maybe?
You might need it on the real, so keep the gain low, kind of like that.
Wait.
Stay on the real axis, so keep the gain just above.
Yeah,
towards-
so that means I can do it. The root locus is telling me I can do it, but I am still iffy. And that's the right answer. Why am I iffy about it?
That might.
That is correct. Because remember, I also want the gain larger than 20. If I make my gain so large, larger than 20, maybe my closed loop pole for that gain would be like beyond the region. Like they will come together and then they go over here and they go a little bit beyond the region. So I don't know. It may or may not work, but it's worth a try. Let's give it a shot. Okay, so we'll try this. And if this doesn't work, what can we do next? We'll talk about it. This is why this is a hard problem. I probably won't give you this hard in the exam, which involves this many tries because you only got so much time, you know. I probably will give a problem where this will just work. But if it doesn't work, we have another trick up our sleeve. So anyway, this may work. Okay, so let's check. Let's give a quick check on this system. The closed loop, how many closed loop poles are there now? There'll be one closed loophole going like this. Other closed loophole going like this. A third closed loophole is there. I'll count that as a closed loophole. So I have three closed loophole coming from this system. Yes, the third closed loophole is going to get cancelled off, but I have three closed loopholes plus one coming from the pre-filter. So my pre-filter still remains what I had before. So I have four closed loopholes, three from root locus, one from pre-filter. The one from pre-filter is at -10. The three from root locus, two are along these lines, and so two of them would be like, wherever they are. One of them is going to be at -2. This closed loophole kind of like stays around there. So there's a closed loophole that's going to start from here. It stays at -2. So now let's talk about the closed loop zeros. Closed loop zeros are the zeros of F, none, zeros of G, none, zeros of K. So I have a closed loop zero at -2. This comes from K. And I have a closed loop zero at -10. So I have two closed loop zeros. So zeros of F, none, zeros of G, none, zeros of K, there is one, and then the poles of H. The poles of H, that's coming from the H. Okay, so effectively what I notice over here is my this closed loop pole, this closed loop pole, and this closed loop zeros are canceling each other off. That's this cancellation. So what am I left with? I am left with 1, 2, 3 closed loop poles, and then, oh, actually two of them are canceling off. This closed loop zero is canceling this closed loop pole. This closed loop zero is canceling this closed loop pole. So effectively, I am just left with two closed loop poles. Okay. So effectively, this is just two closed loop pole system. Two closed loop pole, no closed loop zero. Let me know if this makes sense. It is exactly the system I want it to be. Yes, sir.
Closed loop pole and zero, they're from, that is -10, that's from our pre-filter, correct?
So the closed loop pole coming from pre-filter is being cancelled by the zeros coming from H. The closed loop pole starting from here, which remains around here, -2 closed loop pole, that's being cancelled by the zero coming from the controller. So two of my closed loop poles are being cancelled by two of the closed loops zeros. I am effectively left with just two closed loop poles, which are these main lines. So it's a second order system, a beautiful second order system. So let's give it a shot. Let's find, so now let's do the last step. Let's find the closed loop transfer function. Closed loop transfer function is FGK over 1 plus GK. You'll see that cancellation I was talking about right now. F was 10 over S plus 10. G was equal to 1 over S plus 2. Controller was K times S plus 2 divided by S, like this, divided by 1 plus G, K, and H is 10 over S plus 10. So same stuff divided by 1 plus same stuff. Now, bunch of stuff cancels. So 2 cancels with this. So this 2 cancels with this. And if you do your math nicely, this is going to come out to be 10K divided by S square plus 10S plus 10K. This is algebra, this is math, this is beneath me. You guys handle it. But the idea is that whenever you have a fraction over 1 plus the same fraction, this is basically numerator, this is numerator plus denominator. So if you have a numerator over denominator like this thing, over 1 plus same numerator over same denominator, this basically reduces down. If you multiply on the top and bottom by d, this becomes n over n plus d. This is my secret trick. I've been like being mysterious about it. Just the combined numerator 10 times k. Combined denominator, there is s times s plus 10. This is s times s plus 10 plus the numerator. That's what it is. Okay, so there you go. That's kind of like what I was talking about. My closed loop system has no zeros, only two poles. So this is my perfect closed loop system. If only Jesus can be so kind that when the gain of the controller is 20, I am still within this region. That would be nice. Okay, so how can I check that part? So how can I check the part that when the gain of the controller is 20, I'm not shooting beyond the region? So this is my root locus. When the gain of the controller is 0, I am here. When the gain becomes larger and larger, my closed loop pole is gonna go like this. I really want to make sure that my gain of the controller with the S removed from it is larger than 20. Okay. So I want the limit S goes to 0 of S times the controller to be larger than 20. So I want the limit S goes to 0 of S times, what is my controller? K times S plus 2 over S. I want this to be larger than 20. And this basically means K should be larger than 10. I want K to be larger than 10. If I make, you think the closed loop pole would lie in this region when K is larger than 10, or will it go beyond? What do you guys think? How would we check it?
By assuming some function, by assuming a function where we have.
It's just very simple to check.
Assume both closed loop poles are -5, so it's like 1 over S plus 5 S plus 5.
Even simpler than that. Exactly, just plug this 10 over here and then solve for the closed loop pole and see where they are. If they are within the region, good. If they're beyond the region, we'll talk about feelings later about that. Okay, so let's try K equal to 10. And the closed loop system is going to become 100 over S squared plus 10S plus 100. What is this? Like, what are the solutions of this? The closed loop poles will be minus B plus or minus B squared minus 4AC divided by 2 times A. So minus 5, oh damn. 3, this is gonna be 300 over 4. What is square root of this negative 300 over 4? What is square root of 300 over 4? I need that number. I really want this to work out. Second? I'll just, you know what? It is a number. I don't care. Minus 5 plus or minus I times square root of 300 over 4. How do I know that it's going to be in the region or not? We can check that angle thingy. And cotangent of the angle is the real part over imaginary part. So cotangent of, so if you have a pole, and if the pole's real part is minus 5 and the pole's imaginary part is root of 300 over 4, like this, then check this angle of the pole. So cotangent of the angle is going to be real part over imaginary part. So it would be magnitude of real part 5 divided by root 300 over 4. Check this, if this cotangent is coming out to be less than, or the angle, you can just calculate the angle. Angle is cotangent inverse of 5 over root of 300 over 4. So what does that come out to be?
49.
49?
Yeah.
Okay, so this is not gonna work. When you apply this high of a gain, the closed loop poles are beyond the region. That is extremely unfortunate. I'll never do this to you in the exam, by the way. I purposely took a hard problem. In the exam, it will be like within-ish, so that you are done at this point in time. This will work. But now that we have this situation, let's see if you can help me fix this.
Add a 0, cancel the -10.
Okay, so I have a suggestion that add a 0.
Is there gonna be too many zeros now? No way.
Yes, if I add a 0, then wait, will it be okay if I add an extra 0 in there?
Because we have a
Yeah.
role.
Okay, because pre-filter already has a pole, so controller can handle actually an extra zero compared to this. Oh, wait a minute. If I'm allowed to add an extra zero in the controller, then why don't we just like simply cancel this and make it a straight line? Second. Okay, so let's try this controller now. We'll try a controller which has a gain and integrator. We'll try a 0 at s+2 and 0 at s+10. Okay, so let's try this controller and let's see what comes out of it. And so now the root locus will have 0, sorry, pole at here from the plant, but the controller is 0. Pole at here from H, but the controller is 0. So my root locus is just a straight line. Well, that's for sure gonna get the job done. If you increase the gain, it's gonna stay over there. So this would work. So this for sure would work, but let's try it out. Okay, this controller, I know if I increase the gain, it is always going to remain in this region. I'm not going to have shooting out of the region problem. So let's try this. So my pre-filter is already decided to be equal to 10 over s+10. So let's try this controller. Root locus says it is good to go. So now we just need to do the calculations for this controller. This definitely should work, but let's try it. So the closed loop transfer function now is going to be f times gk over 1 plus gkh. And f is going to be 10 over s+10. G is going to be 1 over s+2. And the controller is k times s+2 times s+10 divided by s. And this controller is okay. Yes, it has more zeros, but then there's a pre-filter. Cancel that 0. So f times k do not have more zeros than poles. So this divided by the same stuff. So this cancel, this cancel, this cancel, this cancels. I'm going to be left with 10k over s+10k. Well, that's pretty. Okay, so therefore I can choose to get the closed loop pole is basically equal to minus 10k. So as the gain k increases, the closed loop becomes more and more negative. So that's the thing. And for the error, I want the limit s goes to 0 of s times the controller to be larger than 20. Let's try what that comes out to be. S. And my controller was k times s+2 times s+10 divided by s. So s times controller should be larger than 20. This s cancels. This is 2, this is 10, they add up to 20. So this basically means the limit of the k should be larger than 1. That's what I want from my error calculation. Sorry, not limit. Limit is already done. This will become 2, this will become 10. So I want k to be larger than 1. If you put k equal to 1, closed loop pole is at minus 10. That works for me. Okay, so therefore try a controller which is just, I don't know, 1.01 times s+2 times s+10 over s. This controller along with the pre-filter 10 over s+10 will get all my job done. Because if k is this, closed loop pole for that k is minus 10, and minus 10 is surely more negative than minus 4. So this meets the closed loop pole. So minus 10 times 1.01 is going to be equal to minus 10.1, like this. So the closed loop pole is in the right region. It has a right angle, it has a right real part. So setting time and overshoot are done. It has a right gain and an integrator. So my error calculations are done. And because pre-filter times controller do not have more zeros than pole, so my use specification is done as well. Sounds good? So this is my controller. I'm gonna shut up. That took whole of the class. I probably won't give you this part in the exam, like up to the previous step was just okay. But this is kind of like the hardest problem, we'll never have to do by this.
Yeah, that's the hardest.
Alright, so now, I'm gonna stop the recording, let me discuss some things with you, in-person people. And then, I'll open up for questions once again and then ask any questions, but give me like 2 minutes for some internal discussions first. Stop the recording.